Hello everyone. Today we are going to see a problem. It is called the longest common substring. Okay, so the problem is pretty simple. We are given two strings A and B. Let's say A is equals to A B B C D A and B equals to X Y B B C A D. Okay, and we need to find a substring which is in both which is present in both A and B, and we need to find the longest such substring. We have to find the length of the longest substring. So this is the problem. Like in this case, the longest substring is BBC. So the answer to the problem will be 3. There are a couple of approaches to this problem. The first one is a dynamic programming solution, or DP, and the time complexity of this solution is O of n square. Second is using rolling hashes, and this has a time complexity of O of n plus m log n. And the third one uses suffix trees, and the time complexity is linear, that is O of n plus n. We won't discuss these two, and in this video we'll see how we can use rolling hashes to solve this problem in O of n plus n log n. Okay, so let's see the solution of this problem using rolling hashes and binary search. So the problem is we have to find the longest common substring. So for any length L, we have to find that is there a substring of length L which exists in both A and B or not. And we can go for L equals to 0 to minimum of n comma m. So we can go to each L and check is there a substring which exists in both A and B. Now this is pretty simple. We can do a for loop, and let's say we have a function, say check, which for a particular length L will tell us is there a substring in of length L in both A and B. Is there a common substring of length L or not? And now what we can do is we can go from 0 to for all the possible lengths we can check if there is a substring, and we can maximize that. The observation here is, let's say we have a substring of length L. Now we can use check to find out whether there is a substring of length L which is common in A and B. And the observation is that if there is a substring of length L which is common in A and B, then for all the lengths less than L, there will also be a substring in both A and B. Now we can see that by in this example we have BBC. This is of length 3. So we can take for lengths 1 and 2, for any length less than L, we can use a substring of this string of length 3. So we can say that if there is a substring of if there is a common substring of length L, then there is also a common substring of length L minus 1. So now here we can use binary search to find this L, and we can maximize between 0 and minimum of n comma m. Now the problem is, how do we find that if there is a substring of length L which exists in both A and B? Now that problem can be solved using rolling hashes. Let's see how it works. Okay, so before going to rolling hashes, let's see what hashing is. So let's say we have a string A B B A. What hashing does is converts this string to an integer, and this integer is unique to this string. To convert this string to an integer, we will use a function. Let's say h of abba will give us a unique integer which will represent this string. Now this function is called a hash function, and this is where we will convert the string to an integer. But let us suppose that we get an integer. Now comparing two strings is an easy job. We can directly compare their hash value, which is the integer which we get after converting the string. Now we can use this hash value to compare two strings. So since this integer uniquely determines your string, therefore we can use the hash value of two strings and compare them. Now this will take O time because we are comparing two integers instead of O of n plus n for two strings. So how do we convert this string? So a very common hash function that we can use is this thing. So h of s, that is the hash value of a string s, is equals to summation of s of I, this is the ASCII value of s, into p raised to the power I, where p is a prime number, and mod. This function will give us that unique integer for a string. Now what will be the values of p and mod? Generally we take p and mod both to be prime, and you should take p and mod both to be prime, because you will get a lot of collisions, and a collision is basically when you get same hash value for two different strings. That is called a hash collision. Let's not get into it, but a good value for p is 31. Now p should be greater than the number of unique characters that are there in your string. So for all the lowercase characters we will have 26 different characters, so 31 is a pretty good value for p. And you can also take 53, and usually we take a small p value. And mod should be large enough, because when we use a hash function and mod it by mod, then the number of different values we can get for all the strings will be between 0 and mod minus 1. So we need a lot of values to distinguish different strings. Normally mod is 10 to the power 9 plus 9 or 10 to the power 9 plus 7. You can use other prime numbers as well. So now what this hash function does is uses this formula and calculates an integer value for your string. Now you can use that integer value to compare two strings as well in O1 time instead of On of, that is the length of the two strings. So for example, let's say we have ABBA. So the hash value of ABBA will be A is 1 into, let's say P is 31 and mod is 10 power 9 plus 9. So this will be 31 to the power 0 plus 2 into 31 to the power 1 plus 2 into 31 to the power 2 plus 1 into 31 to the power 3. This will be equal to the hash of string A, and we'll do a whole mod m. Let's say m here is 10 to the power 9 plus 9. So this will give us the hash value for ABBA. And now let's see some operations on this string. Now what if I want to add a character at the end of the string? So what I want to do is I want to find the hash of s plus d. Now I'm concatenating this d to the string and I want to know the hash of the new string. This is a pretty simple thing. what we can do is, we know the length of the string, which is currently 4. So the length of the string is 4. Okay, so a new string will be this. So its hash for this part will be same, and we just have to add 4 into 31 to the power 4, which is nothing but, then let's say we have a character C. Here C is equal to D. So if we want to add a character, we can simply do C into P raised to the power N, which was the previous length, and we can add this to the hash value of S. This will be the hash value of our new string S dash. So adding a character to the end of the string is simple. We just add C into P raised to the power N. Here P is 31, so we add, and C is D, so the ASCII value of D is 4. So we add 4 into 31 to the power 4, and we add 1 to N as well. The next operation we want to do is deleting a character from a string. So we want to delete the last character of this string. Now this string is S dash now, and we want to delete the last character of this string, that is D. Now deleting is also very simple. What we did was, we added C into P raised to the power N. For deleting, we can simply subtract C into P raised to the power N minus 1, and we can do a N minus minus to change the length of our string, because we have to delete this. Currently our length was 5. After the update our length was 5, so we subtract this value from the total hash value to get the hash value of the string after the deletion operation. So adding a character at the end and deleting the character at the end, we have discussed these two. Now the third part is adding a character in the beginning. So we want to add D in the beginning of the string. So what we'll get after addition will be DA BBA. What will be the hash of this string? This can be done by, so what we are adding, this is D, so we'll do a 4 into 31 to the power 0 plus this whole string. But now if A was at index 0, in this string A will be at index 1, so we have to do a 1 into 31 to the power 1 plus B in this string was at 1, and in this string it is at 2, so we need a 2 into 31 to the power 2 and so on. So what we are doing is nothing but multiplying this whole string by P. Since every character is shifted 1 to the right, so if its index in the original string was I, in the new string it will be I plus 1. So our hash value for the original string was summation of Si into P raised to the power I, and now we know the 0th index part, 4 into 31 raised to the power 0, and for the other strings we need summation of S of I plus P raised to the power I plus 1, and we add the new character into P raised to the power 0. This will be our hash for our new string. So this can be done by taking P common from here. We can take P common, this plus 1 will go away, and this is nothing but the original hash value. So here our h of s dash will be equal to C into P raised to the power 0 is 1 plus P into h of s. and we'll do a n plus plus because we are increasing the length of our string. So if we want to add a character to the starting of a string, we can do this thing. So if you want to add a character at the end of the string, we use this. To add it to delete a character from the end, we can use this. Now we have 3 operations. There is one more operation here. Let's see that. Now the 4th operation we want to do is delete the first character of the string. So we want to remove this a from this string. Okay, so currently we have this 1 into 31 to the power 0 plus 2 into 31 to the power 1 plus 2 into 31 to the power 2 plus 1 into 31 to the power 3. This is the hash value for a, b, b, a, and we want to delete this character, so we need the hash value of b, b, a. Now here what happens is every character in this string will move 1 to the left, so the hash of the new string will be equal to summation of s of I into p raised to the power I minus 1. I goes from 1 to n, and this will be our new hash. So what we can do is multiply and divide by p. So this p will go inside and we get this. Now the hash of the new string will be equal to 1 by p times summation of si to the si into p raised to the power I from I equals to 1 to n. In our original hash value we had si into p raised to the power I for I equals to 0 to n. Okay, so we need 1 to n. So what we can do is subtract the value of a, that is 1 into 31 to the power 0. So we can convert this to 0 to n by subtracting s0 into p raised to the power 0. So we added and subtracted s0 into p raised to the power 0, and s0 into p raised to the power 0 went inside the summation to make it the summation from I equals to 0 to n. Now this summation is nothing but our original hash value, so we can replace it by h of s, which was our previous hash value. Okay, so this will give us the hash value if we delete the first character of the string. Now we have 4 operations on this string. The hash value of the string, we know this previously, we have calculated it. Now if we want to add a character at the end of the string, we can use this function, this formula. If we want to delete a character from the end of the string, we can use this formula. If we want to delete a character from the beginning of the string, we can use this, and if we want to add a character at the beginning of the string, we can use this. Now one more thing, that this division by p is not possible because we are storing the mod values of all these hash functions. The hash values are modded, so instead of doing division by p, you need to multiply this by mod inverse of p. Okay, so you can check out what mod inverse is if you don't know. So for rolling hashes, we need only 2 of these operations. The first one is adding a character to the end of the string and deleting a character from the beginning of the string. So now that we know how hashing works and how we can change the hash values, we can modify the strings, and we don't have to calculate the hash value of the new string, and we can just add and subtract from the new string to modify the hash value of the string. Now let's see how do we solve the original problem. So what we did was use binary search to find the maximum common substring, that is the maximum length of substring which is common in both of them, and we used a function check. What check did was tell us if there is a substring of length L which exists in both A and B. Let's see how this function will work. The most naive thing that we can do here is for each substring of length L in A, we can check if it exists in B or not. This is pretty simple. So for example, we have the case of L equals to 3. The first substring is A, B, B, C, D, A. And we want to check if there is a substring of length 3 which exists in both A and B. This is our B and this is our A. So we can go from here. This is the first substring of length 3. We can check if it exists in A or not. So A, B, B, X, Y, B, it doesn't match. So we can check all the substrings of length 3, and for each substring of B we will do that. If there is a match, then we have found that there is a substring of length 3 which exists in both A and B. If there is not a match, then there doesn't exist a substring of length 3. To optimize this, we can use hashing. What we can do is store the hashes of each substring of length 3 of A. Okay, so we will store the hash of ABB. We will store the hash of BBC, BCD, and CDA. Okay, so let's store these values in a set or a unordered set, whichever you prefer. And now to compare a substring, let's say XYB, we can calculate the hash of XYB and check if it exists in this set or not. This can be done in log of n if we are using a set, and O of 1 if we are using an unordered set. So the time complexity reduces to, for each substring, you find the hash of that substring. This will take you linear time, O of L, and you are doing this for each substring, so O of the length of the string into L, there will be approximately like less than n, but yeah. So you are doing this to get the values of the set, and then you take each substring in this string, that is B. So calculating the hash value will be in O of L again, and for you're doing this for each substring, so the total time complexity will be O of ML. So your total time complexity will be O of M plus N times L, and this is not good enough as well. So now we will use the operations that we studied earlier. The main part here is this part, O of L. What we are doing is we are calculating the hash of each substring again and again, which is quite complex. So of length L, we are going OL again and again to calculate the hash of each substring. Now what we can do is we want to calculate the hash value of all the substrings of length 3. So first we'll get this one, then we need this one, then this one, and this one. So there are 4 hash values that will be stored in our set. So the set will store the hash value of all these substrings. Now calculating for them separately will take a lot of time, so we'll improve on that. So what we are doing here is we have this hash value of ABB. Okay, so the hash value of the next substring is nothing. What we are doing is we have ABB, which is the hash value of our first substring of length 3, and then what we want to do is add C at the end. Okay, and remove A from the beginning. Now this is nothing but the second substring. Again, what we do is add D at the end and remove B. This is BCD, which is our second substring, and the last one will be we add A at the end and remove B from the beginning, and this will be our last substring. Now adding and deletion can be done in O of 1. These operations we have studied earlier. So now we can reduce the time complexity. So what we do, we initially store the hash of the first substring of length L, which is 3 in our case, and for each character that comes after that we can use the operation 1 to add that character to the end, and then the operation and then the second operation to remove the first character of the string, and we will do it again and again until we get to the last index. So this will give us the hash values for all the substrings of length 3. We have calculated the set in which we are storing the hash values for all the substrings of length L of the string A, and we will do it in O of n time using this thing. We add at the end and delete from the beginning. And this thing, adding at the end and deleting from the beginning, is called rolling hashes. Okay, so we can do the same thing for string B. Now we want to check if for each substring in B, is there a hash value which has the same value as this substring? That is there a substring of length 3 which is in both A and B? And we'll do the same thing here. We have the hash value of the first substring. Now we'll delete the last character and we'll add the next character. So we get the hash of the second substring. Now we can check if this substring is in this set or not. Again, we'll delete the first character, add the last character. We'll check if this substring. Now deleting an addition, and on deleting an addition we'll get the hash value of the new substring. Okay, so this hash value we can compare it to the hash values of all the substrings of the string A. So now we can calculate this in O of m time. So the total complexity for this operation, for checking if there is a substring which exists in of length L which exists in both A and B, is reduced to O of n plus m. And our binary search part was of log n time complexity. So therefore the total time complexity of this algorithm will be O of n plus m times log n. Now let's see how we will code this problem. So in the input we have two strings A and B, and we want the longest common substring. So the first part was the binary search. So we'll have our start equal to 0 and our end equals to minimum of a dot size comma b dot size. So the minimum length that we can get is 0 and the maximum length we can get is n. So now the binary search part. So what I did here is not what you'll usually see, but I do this just to be safe. What I do is I find the range in which my answer exists, and that range can have a maximum length of 5. So after that I can directly loop through all those values to get my answer. So you can do your traditional binary search as well, but this is just to be safe, that on which side my answer lies. Is it either end or start? So that. So mid will be start plus n divided by 2, and if check mid, so what I'm doing here is I'm checking if there is a substring of length m which is in both A and B. If there is, then my answer will lie between between mid and end. Otherwise it will lie between start and mid. This is the binary search part, and we need a function check which will tell me if there exists a string of length m in both strings A and string B. Okay, so need A and B. So let's say this function check works. Now what will be my answer? I need the longest substring. So the longest substring, currently my answer lies between start and end. So it will be at least start. Okay, so now I will loop through all the lengths L from start to end, and then check if there is a string of length L in both A and B. If there is, then my answer will be L, and I simply return my answer. So this is a linear part, but it won't take that much time because my start and end, the maximum length from start and end will be 5. Okay, so this will take log of n time. Now the check function. Now what we need is a prime value which is 31 and a mod value which will be 1e9 plus 9. And we will need another prime value. Let's take it 53 and another mod value. Now why are we taking 2 primes and 2 mods? We need only one, right? But we will get into some problem afterwards, and I'll discuss why is that. Okay, so what I want to do is store the hash of all the substrings of length m of in A in a set. So let's take a unordered set. Okay, so my unordered set will contain the substring hash of A. Now what will be my hash value? Long hash my hash value, initially there is no substring, so the hash value will be 0. And for I'll calculate the hash value of the first substring. Okay, so the hash value of first substring, I'll go from 0 to m, and what we are doing here is nothing but adding at the end. So initially our string was empty, now we are adding the first m characters of the string a to get the hash of the first substring. Okay, so what we can do is h is equals to add at end, and what we need here is our previous hash value, and the character that is to be added, which will be a of I. Okay, so let's write this function. So we have long add at end, long hash, and my character C. So I want to add C at the end. Okay, so I also need the length of the string. Okay, the current hash stores the hash for a string. I need to know the length of that string, and the length, let's say, will be n, and we can pass the length n, and here we can do n plus plus because we need to increase the length after adding one character. So the length was n. So what will be the new hash? It will be the previous hash plus the ASCII value of this character will be C minus A plus 1. Okay, and times p1 raised to the power n. Okay, now I need a power function. I will store all the powers of p1 in this power function. Okay, so we need a power 1 function. The maximum length of the string, let's say, can be 1e5, so I won't need a power of p more than 10 raised to the power 5. So I need a power for the second. Ignore the second part, power 2 and p2 and mod 2. We'll get to that later. Okay, so we have a power function, and what we'll return is hash plus the ASCII value of character C into p raised to the power n. Here p1 raised to the power n. My power 1 function stores p1 raised to the power x for at the xth index. So I need to calculate these power 1 and power 2 functions. So let's do that. So I'm doing nothing but I'm taking the power of I minus 1. So let's say p of power of I stores p raised to the power I. So power of I plus 1 will be nothing but p raised to the power I plus 1, which is equal to p raised to the power I into p, which is power of I into P. So I'm using this thing to calculate power of I plus 1. So this is what I've written in. So this will store all the powers of P basically. So if you want to calculate a power of P, you will have to use exponentiation to get that in log of n time, but using this you can get that in O of 1. Okay, so power 2, and we have both the powers. So add at end is sorted now. We need another function, erase from beginning, and we need a hash value, and we need the length. Okay, so how can we do that? Let's see what we did earlier. What we did was so if we have a string, let's say ABBA, and we want to delete this character, we have the hash value of ABBA. We subtracted the hash value of this part, okay, and we divided this whole thing by P. So that is what we will do. We need the previous hash value. We'll subtract the first character of the string, which is C. The ASCII value will be C minus A plus 1, and we divide this whole thing by P, which is mod 1, which is mod inverse of P1 mod 1. Okay, we need a mod inverse function. Let's get that. Okay, so we need the modular inverse of P1 mod 1. Okay, so we can pre-compute this. You can get it online anywhere, or you can use extended GCD to get the mod inverse of P1, and it will be a constant throughout our program. So what I did is calculate this and stored it in inverse P1 and inverse P2. Okay, so now we can replace this by inverse P1. Cool. So what this function will do, what it will do is it will erase from beginning. Okay, so add at end and erase from beginning. These were the two operations that we needed. Now we are storing everything modulus mod, so we need to do one more thing here, mod 1. Okay, and we need to do a plus mod 1, mod 1. Now we have completed these two functions, add at end and erase from beginning. Now let's make it add at 1 and erase from beginning 1, and we need the same for 2. So add it n2. We have our hash. We need power 2 mod 2. Okay, and erase from beginning 2 mod 2 inverse P2 and mod 2. Okay, again I'm not telling you why this 2 is for, but we'll get to that. So initially our length of the string was 0, and we used add at 1 function to get hash 1. Okay, so what this did was create our Okay, so we had a string a b b c d a. What this did was, let's say our here m is here, we have to check for the substring of length m. So it calculated, let's say m is equals to 3, so it calculated the hash for this of the first substring of length 3. Okay, so now we will just insert this substring hash a dot insert hash 1. Okay, now we have stored the hash of this part. Now we need to store all the hashes. So I will go from m plus I. Now I'll go to each character, I'll add it at the end and remove from the beginning. And we don't have to change the length because the length will always be 3. So since we are adding one character, we are doing n plus plus, and then we are deleting one character, we are doing n minus minus, so we don't need to change n. Okay, now for each index a new hash will add at end. The previous hash was hash 1, the character will add is a of I, and n will be n, it won't change. And also will erase from beginning hash 1 character, not a of I minus m. Okay, so remove this character and erase from beginning. So what we did was, if we are at index I, here this index is 3 and the string length is 3, so we added the third character and we erased the 0th character which was at the beginning. At the next iteration we'll add the 4th character and we'll erase the first character which was the beginning of the previous string. Okay, so this will give us the hash for each substring. Now we insert this hash in our substring hashes, and we do this for all the characters. So now we have all the hashes of string A. Okay, hashes for every substring of string A. Now we have to do the same thing again. Hash 1 equals to 0 for the string B. We have stored all the hashes in our substring hash. Now we need all the hashes of string B and compare them with the hashes of string A. So again we'll do the same thing here. Okay, and initially our hash will be 0. For length we'll find the hash of the first substring of length m. This will be the hash we add at end. Instead of ai, now we need b of I. We do n plus plus. We have the hash of the first substring of b. Now we check if substring hash contains this hash. So if it contains the first hash or not. If it is not equal to the end, that is it does contain, just return true. So the first substring is also a substring of A. So now we have the hash, we have checked that. Now for each substring I need to go to each substring after the first substring in B, and we need to check if it contains that or not. So we remove this, instead of A we'll use B of I. Now this will calculate the hash of the next substring, and we do this check. again. Okay, if it contains, return true. Now if we haven't found any string, we simply return false. One more thing, we need to initialize n as well here, because initially the length of the substring will be 0. Now if we run this, yeah, we should get 3, which is BBC. In this case we can check another substring BCDAAB with XYZ BCDABB. Maximum common length is BCD here, so it works. But there is a problem here. The problem is that we are calculating a lot of hashes, so the probability of a hash collision is quite huge. So let's see. Now hashing with, let's say we are doing hashing with a particular mod and some p-value, and we hash 2 strings and then compare them, then the probability of hash collision is approximately 1 by mod. So it is approximately, in our case, 1 by 10 to the power 9. So this is quite low. We won't get a hash collision. But here we are calculating a lot of hashes, so the probability of getting a hash collision is quite huge, and we will most probably get a hash collision, so our program won't work. So what is hash collision? Hash collision is basically there are 2 strings, say s and s dash, which are not equal but their hashes are. Okay, so this creates a problem because this will result in a wrong answer. So we can get around this. There is a way, and to do that we need a second hash value. That is why we have stored p2 and mod 2 and inverse p2 and everything else. All the 2's were to avoid this hash collision. Now what we do is we calculate hash 1 and we calculate hash 2. Okay, so now if both of them are equal, only then we say that this string is equal, and both of them are equal and the strings are not equal, this hash collision is the probability will be quite low and it will work. So now we have solved this question, but because of hash collision we need another thing. We need to do everything again. So we'll store the 2 hashes, one hash 1 with p1 equals to 31 and mod equals to 10 raised to the power 9 plus 9, and we'll use a different p and mod value for our hash 2. And for comparing if 2 strings are equal or not, we'll just use both the hash values and compare if both of them are equal or not. Okay, so what we need to do is we need to store a pair. Okay, and since unordered set can't store pairs, so we'll have to use set here. So we need another hash, and we don't need a n, different n. We will calculate the hash 2. Okay, and instead of inserting just one hash, we'll insert both the hashes. Okay, now here as well we need to calculate hash 2 as well. we need to calculate it for hash 2 and insert hash 1 comma hash 2. Now for the second substring, for the second string B, we also need 2 hashes, and it will be quite similar to that for what we did with A. We'll, instead of finding just hash 1, we'll find both of them, if both of them, this pair exists or not. So hash 1 matches the hash 1 of the first in the first string, that is A, and the hash 2 matches or not. So now we just need to change this to, and again check if both the hashes match or not. Okay, so this should work. Okay, another thing that we missed was this thing. We need to change it to b dot size, because we are doing this in string B. So everything else looks good. Let's try to submit this problem. So this is a problem. This is the same problem that we discussed. A match between two strings is the length of the longest substring which is present in both the strings. So this is the longest common substring. The input is the same as we took. Let's submit this and see what we get. And it's AC. So thanks for watching. Have a good day.